The next question of CodeForces round 923 DIV3 is paint charges. So in this question, we are basically given a array A. So before going into the array, in this question there are n cells. Cell number 1, 2, 3, 4, 5, so on till cell n. Now, now in this we even have an array given. So arrays of length n, a1, a2, considering one base, it's a1, a2, a3, so on to an. Right? So now we can assume that in each of this cell there is a charge. So the charge size is mentioned. So in cell 1 there is a charge of size a1. In cell 2 there is a charge of size a2. In cell 3 there is a charge of size a3. In cell 4 there is a charge of size a4, so on till in cell n there is a charge of size a, right? So now we can use each charge exactly once, or we might not use it also. So we can either use a charge once, or we might not use it, but we can't use a charge more than once. So in each use of the charge, we can do two type of things. So firstly, there are three scenarios. These two scenarios, if we use a charge, then these two scenarios can occur. And this is if we don't, like, if we use a charge, there can be two scenarios. Else, one more scenario is we might not use a charge. I mean, we don't use the charge. Don't use the charge. So firstly, we can either use the charge or no. If we use the charge, then we can use the charge towards the left or towards the right. So let's say we are using the charge towards the left. If we use the charge towards the left, then what happens is it will paint the range from maximum of 1 to 1. So from maximum of 1 to I inclusive. So basically, if we use the charge towards the left, then it will paint every cell in this range. Similarly, if we use the charge towards the right, it will paint every cell in this range. That is I2 minimum of I plus A of I minus 1 to N inclusive, right? So for each charge, there are two scenarios. We can either use it or we don't use it. In case if we use the charge, we can use it towards the left or towards the right only. But we can't use this charge for in both the directions. So we can only use it in one direction. And each charge can be used at most once, not more than once. Now, if we use it towards the left, then it paints all the cells in this range. That is max of I minus AI plus 1 comma 1 to I inclusive. And if we use the charge towards the right, then it paints all the cells in this range. That is I to minimum of I plus AI minus 1 to N. Right? Now, our aim is to use minimum number of charges and paint the whole cell and paint all of the N cells. So our aim is to use of charges and paint all of the cells. Any cells. So this is our aim. So we need to say how many minimum charges do we need to use to achieve this criteria. So we need to print the minimum number of charges required. I mean, this minimum number of charges used to paint all of the N cells. So if you look at the constraints, here test cases can be in the range 1 to 100. N can be in the range 1 to 100. And each AI value of the cell can be in the range 1 to N. And here it's even guaranteed that summation of N over all test cases won't exceed 1000. So summation of N will be less than or equal to 1000. So let's see how we can solve this problem. So the prerequisite for this question is dynamic programming. So it is like you should be good with dynamic programming. So firstly, let's look at the DP definition. DP of I of left of right. So this is what our DP definition is. This is what the DP state is. So assuming that this DP is built on cells considering one-based indexing. Considering one-based indexing. So basically, it's built on cells considering one-based indexing instead of zero. So now DP of I of left of right tells us using first I charges what is okay using first I charges left is the first unpainted cell from left to right. From left to right, that is from 1 to n, and right is the first painted cell from right to left. That is from n to 1. Right? So using first I charges, left is the first unpainted cell from left to right, and right is the first painted cell from right to left. So this gives us the minimum number of charges to reach this state. So using first I charges, left is the first unpainted cell from left to right, and right is the first painted cell from right to left. What are the minimum? How many minimum charges were used? How many minimum number of charges were used? to, to reach this states, to reach these states. So basically the definition is like we used first I charges, and left denotes the first unpainted cell from left to right, and right denotes the first painted cell from right to left. So to reach this state using I charges, how many minimum charges did we use among the I charges is what dp of I of left of right stores. Right? So how many minimum number of charges were used among the first I charges? Right? So this is what our DP definition is. So if we look at our DP space, let us consider the DP space as DP of n plus 1, as we are considering one based indexing, and number of left points, let us consider n plus 2 points, and right as n plus 1. So let's consider this as our DP space. And why did we take this as n plus 2 is in our transitions, we'll be handling one of the case where the value can go more than n plus 1. So just to handle that scenario, we are considering the DP state as we are considering the size of left as n plus 2. So this is how the DP state looks like, and this is the definition of our DP. Now let's look at the base condition. So our base condition is initially number of elements, initially number of charges we used are 0. Using 0 charges, the first unpainted cell from left to right is 1, and the first painted cell from right to left, the first painted cell from right to left is 0, right? Here basically we just saw that while defining our DP, we were defining our DP considering one based indexing, right? So as there is no cell from right to left painted till now, we are denoting 0 as the cell which is imaginary. So we are just assuming that like 0 basically right will be 0 if no cell is painted from right to left. That's what we are assuming. So DP of using 0 cell, using 0 charges, the first charge that is unpainted from left to right is 1, and the first painted charge from right to left is 0. As there is no painted cell from right to left, we are denoting that as 0. Okay? So this will be 0. And apart from this, apart from I is equal to 0, left is equal to 1, and right is equal to 0, rest all DP of I of left of right let's denote it with some large number called as infinity. Because initially we couldn't reach any of these states. We could only reach this state. Right? So this is what the base. This is the base condition of DP. That is using zero number of charges. The first unpainted cell from left to right is 1, and the first painted cell from right to left is 0. As there is no painted cell, we denoted it with 0. Now let's see the transitions of DP. So while in the transitions, let's make transitions for the following. Our aim is to calculate dp of I of left and right. So this is what we need to calculate. And let us assume that we already know the answers for dp of I minus 1 of left to right. So we already know the answers of dp of I minus 1 of left and right. Any I minus 1 left and right combination. This is already calculated. Okay. So now in the transitions, there can exist three type of scenarios. First scenario is using charge I towards the left. So this is the first scenario. Second scenario is using charge I towards the right. Third scenario is don't use the charge. Don't use ith charge. That is skip ith charge. Skip charge I. Okay. So these are the three scenarios. So now let's see for the first scenario how we can calculate dp of I of left of right from dp of I minus 1 of any left and right. So now the first scenario is using charge I towards the left. Right? So if we are using charge I towards the left, then the range that we'll be painting. So in the question, it's mentioned that we can paint a single cell multiple times also. So the range that we are painting here is, let's calculate the left point of the range. Left point of the range will be minimum, maximum. As we are using this towards the left. So it would be maximum of I minus AI plus 1, comma 1. And the right point is I. So if we use ith charge towards the left, then we can paint the following range from left point to the right point, cells from left point to right point. Right? Now here the claim is, let's say we have some cell which is not painted. So there is one small greedy claim while making the transitions. Greedy observation. Yeah. One small greedy observation while making the transitions is, let's say left is the point from left to right, which is the unpainted cell from left to right. Let's denote left as the unpainted cell from left to right. Then it is always useless performing an operation. Let's say we are at some I which is greater than we are at some charge I which is greater than left, then the claim is it's useless performing a left operation. I mean, basically, it's useless using charge I towards the left towards the left. It's useless using charge I towards the left if the range covered by ith charge. Let the range covered by ith charge be L and R while we paint. Then it's useless to paint use the ith charge towards the left if L is greater than left. Right? This is because we can consider a scenario here. Let's say we have some cells over here. Now, let us say this is the cell which is not painted. This is the cell which is not painted. Right? Or let's say all these cells are painted. Right? And this is the cell which is not painted. Now, if we are at some ith point, right? Now, in case if we paint from the ith charge, like if we use the ith charge towards the left, and let's say if we could paint only this region, then in the future, however, we should use one charge I to paint this whole region, right? So if we are using some ith charge to paint this whole region somewhere in the future, then this whole thing will become a subpart of this whole range. So from this, we can observe that it is useless using this kind of charge, which couldn't, when we are using a charge towards the left, if that charge couldn't paint the first unpainted cell from left to right, then it's useless using that charge. Why? Because in future, for sure, we'll use a charge with a higher cell towards the left to paint this unpainted cell if we couldn't paint a cell from the ith charge, right? So from this greedy observation, we can conclude that use ith charge towards the left only if we could paint the unpainted cell from left to right. Only if we could paint the unpainted cell from left to right. Right? Otherwise, it's useless using that charge towards the left, as we proved it from this. So, because that is the scenario, the transition will look like, when can we say we could paint the leftmost cell, which is unpainted, from left to right? We could say we could paint that cell only if left is greater than or equal to the left point. That is, the current left point's range is smaller than the left. Then we could paint it, right? So in this case, the transition will look like dp of I. Now, if we see what will be our left point, so we can say that our left point will be max of right point, comma, the right plus one, right? Why? Because we know the the current painted cell from right to left is basically it looks like this if we consider the diagram. So let's say these are the cells which are already painted, and this is an unpainted cell. Now let's say somehow we painted some of the cells over here, right? Something over here. And let's say something like this. So we have painted using this cell towards the right, let's say. Now we are making decision on this, and we are using this cell to paint it towards the left, right? So if we paint towards the left, now what happens is, let's assume that the range of this is till here. Then we'll be painting this holes, all of this. After painting all of this, what happens is the next unpainted cell from left to right, the smallest unpainted cell from left to right will become this, right? Because now we just merged the right part and the left part. That's what happened. And one more scenario could be like we might not have used it, and let's say we use some right part, and the right part is we use the right part to paint only this part. Okay? So in this scenario, when we paint this whole thing, the next unpainted cell from left to right will become this. Okay? So to handle this scenario, we are doing max of RP, that is right point of the range, comma right. Right will give us the rightmost painted cell, that is from right to left. What is the first painted cell? Plus one, right? And one more scenario is we use this one to the left, and now we are using this one to the left, and we are merging it, right? So when we merge it, this point should be the next unpainted cell from left to right. So these are the scenarios. To handle all the three scenarios, we are doing this. That is max of right point, comma, right plus one. So if you see, all the three scenarios are handled by this. So this will be the next unpainted cell of what is the next painted cell towards the right. So we can say the next painted cell towards the right will be max of right point, comma, the current right. Right? So that is because even this we can analyze it with the diagram. So let's say this cell is all, this part is already painted, and this is the point which is unpainted. And now we made decision, we are making decision over here. Right? Now, if we see in this scenario, the next unpainted cell, the next painted cell from right to left will become this, right? Whereas one more scenario is, let's say we have used this cell towards the right, and now we are using this cell to paint towards the left. Then we'll be painting this whole part. That is, we'll be painting from this till this, let's say, in case if the range is like this. Now in this scenario, the next painted cell from right to left will become this, right? So that is why the next left, basically the next unpainted cell from left to right will become max of right point, comma, right plus one, and the next painted cell from right to left will become max of right point, comma, right. So these are the two scenarios to handle the next painted cell from right to left. And by doing this, we can handle both the scenarios at once, right? So this is equal to minimum of dp of I of max of right point, comma, right plus 1 of max of right point, comma, right. Right? Comma, now dp of I minus 1, basically from dp of I minus 1 of left, comma, right, from that state, we could come to this state, right? So that is why after performing one operation, because we are using the ith charge, so the value of dp of I of max of r3 comma right plus 1 of max of right point comma right will be equal to dp of I minus 1 of left of right plus 1, right? Plus 1 because we are using the current charge. So as we are using one charge, number of charges we use to reach this state plus the ith charge which we are using towards the left. So this is the transition after making the greedy observation when we use the ith charge towards the left. Right? Now let's see using ith charge towards the right. So if we use the ith charge towards the right, then firstly, let's see which range will get painted. So left point of the range will be I in this case, and right point of the range will be minimum of I plus AI minus 1, comma, N, right? This is what will be the right point. So now let's see the transitions. So here there are two scenarios. That is, if left point is less than or equal to the current left, right? So here we are making these transitions considering ith charge, left, like considering we already know the answers for dp of I minus 1 of left of right, right? Considering this is already calculated, and we are calculating every dp of I of left of right. So now assuming using I minus 1 charges, left is the point which is unpainted from left to right. First point which is unpainted from left to right. Then if the range that will be painting if we use ith charge towards the right, the left point of that range, if that is less than or equal to left, then we can say that we'll be merging, we'll be merging the left point which was unpainted, right? So if we look over, let's take a scenario and then look over it. So let's say we have painted this and this was our left, right? Let's say this was our left. Now, let's say we are using this I and then painting it, right? If we use this I and then if we paint it towards this point, basically we are painting it towards the right. So let's assume that till here the range is. So we are painting it towards here, right? Now if we see, previously this cell was unpainted, right? Now it got painted. That means now the the leftmost cell which is unpainted from left to right will become this cell, right? So in this scenario, the leftmost cell which is unpainted from left to right is changing. Right? And similarly, if we consider I to be this point only, let's say though I is this point, still same thing occurs, right? That is, we'll just paint this one till here. So we can observe that now also the uh, leftmost, first leftmost cell which is unpainted from left to right got changed. Got changed and now it is this, right? This is the first leftmost cell which is unpainted. And the painted cell will become this. So, like to handle these two scenarios, we can just write. So to handle these two scenarios, we can just handle it in a similar way how we did for the previous case. So because the left point is getting merged now, and the left is changing, it changes as follows: dp of I of, in this scenario, dp of I of max of right point, comma right plus 1. So left can become this, and right will become max of right point, comma right. Right? This is equal to minimum of I dp of I plus 1 maximum of right point, comma right. Right? So we are calculating the value from dp of I, from the state dp of I minus 1 of left of right plus 1. Right? So this one, because we are using the current ith charge towards the right. So this is one scenario, and this is how the transition looks like for this scenario. Else, if this is not the case, then the claim is rightmost charge won't change. Sorry, leftmost charge won't change. Like basically, not leftmost charge, leftmost cell won't change. That is basically the leftmost cell which is unpainted from left to right won't change. So we can see that with the same scenario. Let's say we have painted this till here, and the leftmost point which is unpainted till now is this. Now, in case we are using some I over here. Yeah. So now let's say in case we are using some I over here, right? Then we'll be painting it towards the left, towards the right, right? So here we can observe that this charge will never change. This is never changed. Leftmost charge will remain the same, but rightmost charge, rightmost cell which is leftmost cell will remain the same, but the rightmost cell which is painted from right to left will change, right? And that will just become maximum of right point, comma right. So from this, if we draw the next steps, then dp of I of right of left because left is not changing, of max of right point comma right plus 1, sorry, max of right point comma right will be equal to minimum of, as we want to minimize our answer, dp of I of left of maximum of right point comma right comma dp of I of left of right, dp of I minus 1 of left of right, dp of I minus 1 of left of right plus 1, because we are using the current charge towards the right. So it is plus 1. So number of charges we use to reach this state plus 1, the current charge. So these are the two scenarios if we use the ith charge towards the right. Okay. Now the only thing left is skip the ith charge. So in the case of skipping the ith charge, the transitions will look like ith charge. So because we are skipping the ith charge, there won't be any change between the left and right states, right? So in this scenario, dp of I of left of right will be equal to minimum of dp of I left of right comma dp of I minus 1 of left of right. And we are not using this charge, so we need not add a 1. So this is how the transition looks if we skip the current charge. Now the answer would, now once we process this, our answer will be dp of n plus dp of n so basically it is minimum value among dp of or we could just say the answer is dp of n plus 1 of n, right? This will be our answer. So this means using n charges, using first n charges, the leftmost unpainted cell is n plus 1, and basically the leftmost unpainted cell from left to right is n plus 1. That is, this just means that we painted all the n cells, right? So the leftmost unpainted cell is n plus 1. Because there is no unpainted cell from left to right, we are treating it as n plus 1. So using first n charges, the leftmost unpainted cell is n plus 1, and the rightmost leftmost unpainted cell is n plus from left to right, and the rightmost painted cell is n from right to left. The minimum number of charges we use to reach this state is stored in this. Okay? So that will be our answer. So if we look at the, so this way we can solve the problem using a 3D DP. And if we look at the time complexity of this, it is big O of n cube. We can say it is big O of n cube, as we use 3 states here, 3 n size states. Space complexity will be big O of n cube. This is per test case. And this is sufficient enough to pass in the given. Here it is even guaranteed that summation of n is at max 1000. So we can assume there is 10 test cases. There are 10 test cases given with n as 100. This will be the worst case. And this is still sufficient enough to pass in the given time limit. So for this question, 4 seconds is the time limit given. and the current time complexity is sufficient enough to pass in 4 seconds of time limit, and space limit is 256 MB. So n cube space per test case is sufficient enough to pass in the given memory limit as well. But in case if you want to optimize the space, here we can observe that the space could be optimized furthermore, though this is sufficient for the given TL and space complexity. Let's just discuss how we can optimize the space. So we can bring down the space to big of n square. So the hint to bring down the state to big of n square is, we can see that dp of I of left of right. So dp of I of left of right. So for any I in this range, for any left in this range, and for any right in this range, for any I in this range, for any left in this range, and for any right in this range, right is from 0 to dp of I of left of right depends on dp of I minus 1 of some left and right. So here we can see that every dp of I just depends on I minus 1. So when we are at some I, we don't care about the information of I minus 2, I minus 3 and so on, which we calculated, which we computed. So what we can do is, we can pick only two dp's. NDP will tell us the next dp, which refers to dp of basically NDP of left of right will tell us will be equivalent to dp of I left and right, and dp of left of right will correspond to dp of I minus 1 left of right. So at every point, maintain only two dp's, that is next dp and the previous dp. So here ndp will refer to dp of I of left of I for every I. For any I, ndp should refer, like implement in such a way that for any I, ndp of left of right should be equivalent to dp of I of left of right. Similarly, dp of left of right should be equivalent to dp of I minus 1 of left of right. So in our logic, whatever these things were, these two things should refer to those. So implement in such a way. So here by just taking two, by just taking two arrays of size arrays or lists of size n plus 1 of n, we could just compute the same transitions which we discussed here by just ignoring one state, which is this. So because we are ignoring that state and implementing it using only two arrays or lists called NDP and DP, we can say that the space complexity will reduce down to big of n square as we cut down one whole state only, which is of size. Right? So in this case, time complexity remains the same. Space complexity will be big of per test case. So this is how we can optimize the space. So this is how we can solve the problem with TL of n cube and space complexity of n cube or n square, depending on how you implement.